Okay, let's take a look at why we breathe. Cellular respiration plays a large role in it. Okay, so if you remember, we have glucose, which is going to be our $10 bill. And we've got oxygen, and that glucose gets hydrolyzed into 2-pyruvates. And each of those are $5 bills. And then we've got the mitochondria, powerhouse of the cell. This is where all the magic happens, right? Okay, we're skipping all the intermediate steps. All right, these guys go into mitochondria. So does oxygen. So 2 things go into mitochondria: glucose and oxygen. 3 things come out. And we've got CO2 and water and lots of ATP, depending on how you count it. Go with 34. Okay, so you put in $10 of glucose in the presence of oxygen, and you come out with 34 quarters, which is pretty good. Okay, it's basically mitochondria is basically functioning as a change machine. Now remember, this is aerobic cellular respiration because we have oxygen. Okay, now here's where the fun starts. Okay, and I literally enjoy this. Okay, so if we let CO2 combine with water, pencil's about to break. Okay, they're going to combine with water, and they're going to form H2CO3, which is carbonic acid. Okay, now that carbonic acid rapidly splits and forms HCO3 minus, and something very special. Okay, so remember, conservation of mass, conservation of matter. Let's treat these as 2 separate equations. Okay, let's treat CO2 plus H2O gives you carbonic acid. So over here on this side, we've got 1 carbon over here, 1 carbon over here, 1, 2, 3 oxygens over here, 1, 2, 3 oxygens over here, 2 hydrogens over here, 2 hydrogens over here. Okay, so our math is good on this side of the equation. Now let's go from carbonic acid to this guy and this guy. Now this guy over here is bicarbonate. Okay, HCO3 minus. And let's figure out what this guy is by using our knowledge of chemistry. Okay, let's start over here. We've got 1 carbon. So remember, the same atoms, the number of each atoms on the carbonic acid side of the equation must equal this side of the equation. All right, so we go with 1 carbon here, 1 carbon there. All right, that checks out. All right, 3 oxygens here, 3 oxygens here. Okay, that checks out. 2 hydrogens here. Oh, only 1 hydrogen here. That means that this unknown substance must be a hydrogen. And because this is an anion, okay, that means that this has to be a cation to balance out, because carbonic acid over here does not have a net charge on it. Okay, so that means that our missing substance over here is H+. Okay, so if we do a lot of cellular respiration and we're cranking out tons and tons of CO2 on this side, we're going to drive the equation over here to this side. All right, so if our concentration of CO2 in the bloodstream rises, that means our concentration of H+'s rise. Okay, so the other name for H+'s is hydrogen ion, or simply proton, because hydrogen is the first element on the periodic table, and it has 1 proton and 1 electron, and if we ionize it and take away the electron, we're left with 1 proton. because it has no neutrons. So these are protons. Okay, now what does this mean? Well, we have a scale called the pH scale. And over here, we've got pure acid. And over here, we've got pure base. Okay, and right smack here in the middle, we've got 7, which is neutral. There are no units for the pH scale. Okay, it's a measurement of acidity or alkalinity. All right, so pure acids tend to have a whole lot of H pluses, or actually just H pluses. Pure bases, so these guys are cations, and these guys are anions. These guys have a lot of OH minuses over here if you're a base. Okay, I just have the same number just for, okay. And if we take one of these H pluses over here and one of these OH minuses, so pH of 0, pH of 14. Take one of these guys and we plop it down right there. So H plus plus OH minus, 1, 2 hydrogens, 1 oxygen, plus and a minus cancel out, and you get water. All right, with a neutral pH of 7. Now, our arterial blood, it's got to be arterial. We'll explain why some other day. Our arterial blood has a pH range of 7.35 to 7.45. And again, there are no units. Okay, so we've got a range here. It's a pretty narrow range. So the thing is, the more CO2 that builds up in our bloodstream, the more protons, the more H pluses there will be. Well, that means we are driving our pH down from 7.35 to 7.45. We're driving it down. We're never going to hit 0, but we're making it more acidic. So a rise in serum CO2 corresponds with directly with a rise in serum H pluses, which will directly drop our pH. And you might be like, well, what's the big deal with that? Well, okay, and it has to do with cooking. All right, it all comes down to cooking, actually. When you marinate steak, when you marinate chicken, when you marinate any kind of actually tough meat overnight, you marinate it not only for taste, but also to tenderize it, because acids tend to break down proteins, okay? And that's why you can marinate in stuff like Italian dressing or orange juice or anything that's acidic will break down proteins, okay? And hey, we call that denaturing. All right, when we break down proteins. So by cooking your food, by cooking and marinating your food, you're doing two things. You're adding heat to the food and you're dropping the pH of the food, and these two together do an awesome job of denaturing proteins. So if we don't get rid of these H pluses that are building up in our bloodstream, you're pretty much marinating yourself from the inside. And the problem with that is that the proteins that are in your bloodstream, like, I don't know, like maybe hemoglobin, is going to break down. It's going to denature. And if you don't have hemoglobin, don't have enough hemoglobin in the bloodstream, you can't carry oxygen, you can't carry CO2. It's kind of an important protein, okay? And that's just one of thousands of proteins that you need, okay? So if only there was a way to get rid of H pluses. There actually is, because they're directly proportional. If we can get rid of the CO2 and bring this back down, that means we're going to drop our hydrogen ion concentration, which means we're going to bring our pH back up to normal, 7.35 to 7.45. And this is why it's so important to get rid of the CO2 in your bloodstream. And how do we do that? We transport it up to your lungs. We cross the simple squamous barriers from the pulmonary capillaries into the alveoli, and we exhale the CO2. So the reason why we breathe is actually to get rid of CO2. And the reason that we know our CO2 in the bloodstream is high is because we have chemoreceptors that sense the pH of our bloodstream. They actually measure the pH of the bloodstream. They don't technically measure how much CO2 there is, but they measure the pH of the bloodstream. And when the pH is dropping, the brain can then integrate all those impulses from the chemoreceptors that are sending impulses through afferent sensory pathways, and the brain can then integrate it and say, wow, pH is dropping. Uh-oh, I'll bet you that's because H pluses are building up. Uh-oh, I'll bet you that's because CO2 is building up the bloodstream. Uh-oh, let's get rid of CO2. So we're going to increase the respiratory rate. So we're going to breathe. And that's why we take a breath. We do not take a breath in order to take oxygen in. The chemical changes that prompt us to breathe are because our blood is becoming acidotic. Okay, so that's why we breathe. Now, there's a little bit more to the story too. Hey, what happens if we're low on oxygen? Like, oh, I don't know, if we are bleeding out and 20% of our blood is laying on the pavement, that means that we can't do aerobic cellular respiration. So that means that we can't do this as efficiently. And that means that these pyruvates are not going to go into the mitochondria. These pyruvates are going to get converted to lactic acid because we're going to do lactic acid fermentation. And now, instead of putting in a $10 bill of glucose and getting 34 quarters of ATP out, you're putting in a $10 bill of glucose and you're getting lactic acid and only 2 ATP, which really, really, really stinks. But it's better than nothing. $10 of glucose is getting transformed, the energy is getting extracted, and you're getting 2 ATP as a result. But you're also getting lactic acid, which is going to further drive your pH from being 7.35 to 7.45. You're dropping your pH, okay? And this, again, is why we breathe. When pH drops, we need to get rid of CO2.